Hello class, in this video we're going to learn about minimum spanning trees and what is Prim's algorithm. The learning intention of this video is for us to develop an understanding of a few terms. So we're going to understand what trees, spanning trees and minimum spanning trees are, for us to understand what are the applications of minimum spanning trees, and to learn how do we find the minimum spanning tree of a network. So the first thing I want to go through is defining these three words over here. We say that a tree is a connected graph that contains no loops, multiple edges, or cycles. In networks, we use trees in applications where we need to try to connect towns with electrical wires or water supply networks. So let me show you some examples of what trees may look like. So in the following examples over here, notice that they don't contain any of the following properties at all. And in the third example, this is not a tree because it contains at least one of these following traits over here. The reason why we cannot have a loop, a multiple edge, or a cycle in a tree is because that in application questions, this is seen as a waste of unnecessary wiring or piping. In other words, this means that it is redundant and involves extra unnecessary costs associated with it. An important property of a tree is that it will always contain one less edge than the number of vertices. So this can be represented by this mathematical relationship over here, where the number of edges is equal to n minus 1, where n represents the number of vertices. So if you look at the first example down below, notice over here contains 1, 2, 3, 4, 5, 6, 7, 8 vertices. So if you're going to therefore draw a tree, it should therefore contain 7 edges, one less than that. Similarly, in example number 2 over here, it contains 11 vertices, so therefore the number of edges that this tree should have is going to be 10. Let's now look at what a spanning tree is. A spanning tree is a specific type of tree where it connects all of the vertices in a connected graph with the least number of edges. Remember, the least number of edges is always going to be one less than the total number of vertices. Furthermore, it is also possible to draw more than one spanning tree for a given network. So let me show you an example of this. So I'm going to try to draw a spanning tree for this particular network over here. Notice that in this network, I have 7 vertices. So when I'm trying to draw a spanning tree for this network over here, I can only have 6 edges. So one less than the number of vertices. So one of the ways that I could go about this, where I have to connect all of the vertices, is like so. Please note that in my spanning tree, I have no loops, multiple edges, or cycles at all. Another way that I could draw a spanning tree for this network over here is something like this. And this just further reinforces that you can draw more than one spanning tree for any network. Let's now talk about what is a minimum spanning tree. A minimum spanning tree is a spanning tree with the minimum combined weight overall in that particular network. So if you look at the example down below, I've got the original graph over here, and on the right of that, I've listed down 3 different spanning trees that I could make for that particular network. In order for me to find out what is the minimum spanning tree, what I do is I find out the overall combined weights. So what I'm going to do now is I'm going to add up all the weights for that particular spanning tree. And if I do that, notice that in the third example over here, this contains the lowest weight out of all of them. So we therefore say that this over here is the minimum spanning tree for that particular network. I do also want to point out that you can actually have many minimum spanning trees for a particular problem, but in this particular case, there's only one minimum spanning tree, which is why I put an asterisk in the notes. When you're dealing with complex networks, finding the minimum spanning tree can be difficult because we know that you can have multiple spanning trees, and finding out the combined weights will be very time consuming and ineffective. This is demonstrated in the example down below. So I could find out what is the minimum spanning tree by drawing all the spanning trees for this particular network and then finding the overall weight of that. And so therefore I could say that the third example is going to be the minimum spanning tree. However, there is a better systematic way for you to find out what is the minimum spanning tree, and that is conducted via Prim's algorithm. So let me explain how do we apply Prim's algorithm to find the minimum spanning tree. Before you even apply Prim's algorithm, it's important to note how many edges you should have for your minimum spanning tree. So in this example over here, because you've got 6 vertices, you should only have 5 edges when you're drawing your minimum spanning tree. Now let's start off with step 1. Step 1 says to choose any starting vertex. The starting vertex that I personally like to choose from is the one with the lowest weight possible. So in this example over here, the lowest weight is the value 2, and therefore I can start from either vertex A, B, E, or F. In this example, I'm going to start from vertex A in this case over here. Step 2 reads, walk along the shortest edge from the starting vertex until you get to another vertex. So in this example over here, the shortest edge or the shortest weight has a value of 2. So I'm going to walk to B. Step 3 reads, find the next shortest edge from any of the connected vertices to a new vertex. So therefore, I can start from vertex A or vertex B, and I want to connect to C, D, E, or F. The next lowest weight that I can see has a value of 5. So what I'm going to do is therefore create an edge connecting between vertex A and D. And then I'm just going to repeat all these steps over here until all the vertices are connected. And if I have done this correctly, I should have only used 5 edges for my minimum spanning tree. Let's now find out what is the next shortest edge that I can go on to. So the next shortest edge I can see has a value of 3. So I'm going to go up from D to C in this case. All that's left is for me to connect to vertex E and vertex F, and the next shortest edge that I can see has a value of 6. Because both of the values are the same, it doesn't matter which edge that I create. So in this example over here, I'm going to go between vertex D to E, and therefore to connect to the last vertex, I'm going to go from E to F. To quickly double check my answer, I'm going to make sure that I've got no loops, multiple edges, or cycles at all. And I can see that I don't have any of that. And I also have 5 edges. So I've drawn this correctly. So now that I've done this, all I need to do now is add up all the values. So adding up 2, 5, 3, 6, and 2 should give you an answer of 18. What I'd like you to do right now is have a go at drawing your own minimum spanning tree by applying Prim's algorithm. So have a go with this question and we'll go through the answers together. So again, first thing that I normally like to do is I want to state out how many edges that I should have for my minimum spanning tree. So in this case, I should have 6 edges because I have 7 vertices. Now that I've done that, what I'll do now is I'm going to locate what is the smallest value. So the smallest value in this network is 5. So I could either start from vertex A, D, C, or E. In this example, I'm going to choose from vertex A and I want to walk down the shortest edge. So I'm going to go from A to D. The next thing to do is find out the next shortest edge and connect to another vertex. So the next shortest edge has a value of 6. So I'm going to go from D to F and I'm going to keep repeating on this process. The next shortest edge I can see is going from A to B because that has a value of 7. So I'm going to walk down that way. All that's remaining is vertex C, E, and G. The next shortest edge connecting to those vertices has a value of 7. So I'm going to go from B to E and then I'm going to go up from E to C because that has a next smallest edge of 5. And the last thing for me to do is connect to vertex G. So I'm going to go from E to G. To determine the length, all I'm going to do now is add up all the weights. So if you do this correctly, you should have an answer of 39. Have a go with the last question where you need to find out what is the minimum length of cables by using Prim's algorithm. For this question, I'm going to locate what has the lowest weight. So the lowest weight is 15. So I'm going to start from the main server and I'm going to walk down to vertex D. The next lowest weight that I can see has a value of 28. So I'm going to go from D to E. From there, I can see that the next lowest weight has a value of 30. So I'm going to go from E to G. The next smallest number that I could see has a value of 32. So I'm going to go from G to F. All that's remaining is to connect to vertex A, B, and C. So the next smallest value that I could see has a value of 35. So I have multiple options. I could either go from A to E or C to G. In this example, I'm going to go from E to A or A to E. And then I'm going to go from A to B because that has a next smallest value of 28. And lastly, to connect to vertex C, I'm going to choose 35 because that has the smallest value. So I'm going to go from G to C. So therefore, by adding up all these values on those edges, it should give you an answer of 203, which corresponds to option B. By now, you should be fairly confident at applying Prim's algorithm to find the minimum spanning tree. So what I'd like you to do now is to answer the 3 questions found on exercise 14E. This is the end of the video. Thank you guys for watching and I'll see you guys again in the next one. Bye.